Certifying quantum enhancements in thermal machines. Let's listen to him.
So hello, and as he correctly said, I'm Jose Antonio Almanza Marrero. I will show you I'm a last year PhD student at the Institute for Cross-Disciplinary Physics and Complex Systems in Mallorca. Today I will talk to you about, again, because I think we have touched this topic a couple of times during the conference, about like quantum thermodynamic, let's say, enhancements against classical thermodynamic devices. But in this case, I will focus in one specific type of thermal machines that are like quite different to the ones that we have considered. Here is missing a word that is continuous, because the thermal machines that we are going to consider are continuous devices. Let's say they are going to be physical systems that are operating in a non-equilibrium steady state, and they will perform a thermodynamic task like refrigeration or gas producing work. And basically, if you think about a quantum thermal machine and you want to somehow certify any kind of advantage over a classical device, what you can first look is that can this machine do something that any classical machine can do? And this would be, for example, you can go and check a classical bound on thermodynamic quantities and see if this machine can somehow overcome this. For example, since when you have quantum thermal machines or stochastic classical thermal machines, you have a microscopic system in which thermal and quantum fluctuations are they are important. They have to take into account. So you have to, apart from averages like work, heat, efficiency, and production and everything, you have to look at fluctuations. So you can go there and, for example, see if you check the thermodynamic uncertainty relation, which is basically a well-known result in stochastic thermodynamics that tells you that precision in any current of a given classical system is bounded by the dissipation, let's say the entropy production in the steady state. So here it's basically telling you that this quantity have to be bigger than 2 in any classical system, which is basically that if you want to be more precise up to a certain point, you have to dissipate more energy, you have to be less efficient in a thermodynamic sense. So this can be used as a witness. For example, if you design a quantum thermal machine and then you can go below this limit, you can for sure certify that this device is not going to have any classical counterpart. But then you can have you can be in this zone, for example, in which you are fulfilling this inequality, in which this witness can become a little bit like obscure, because you cannot say, of course, here who is going to be the better, the classical, the quantum one, you cannot know. And this here in this zone is where our approach is going to be like more important, let's say. So in this talk, basically what I want to address is the problem of, if you want to certify a thermodynamic advantage, you want to design a proper classical counterpart, in the sense that if I give you some thermodynamic resources, let's say temperatures, and I give you a bare Hamiltonian for a system, what will you do? And I tell you, I want this amount of work. You will construct a classical device. You will construct a quantum device. What will you do? This is our goal, let's say, to answer this question. And for answering this, you have to ask, okay, what is the main difference between these two cases? Probably is coherence, no? And then it's a good moment to we are going to create now a catalog of different steady-state coherence that we can have in these devices. Okay, since our systems are open quantum systems, they are going to be described by the Limblad-Noster equation. And in this kind of dynamics, you can have in the steady state, if you do some kind of architecture, some coherence that can survive to the decoherent process. It can be because you can have a Hamiltonian driving, you have a driving, and then in this case you can have coherence between different energy levels, of the Hamiltonian, and we will call this energetic coherence. Then you can have, for example, an autonomous machine in which you put and you engineer some kind of many-body interaction between the states of the Hamiltonian, and then you can have also Hamiltonian-induced coherence, but in this case, it will be generated by many-body interaction. And then you can have a final, let's say, special case, which is noise-induced coherence, that is generated by environmental noise. Basically, it's that since your system is quantum and you have some transition between two levels that are not distinguishable by the bath, once these transitions happens, you can fall in a superposition. So in this case, even without any, let's say, perturbation in the Hamiltonian, you could have a steady-state coherence. So these are the three main cases that we are going to study, basically. Now we have to look at how you would define a good classical analog. So I would define a good classical analog, for example, if for making a fair comparison, it would be that I want that the two systems have the same incoherent resources, let's say the same temperatures and the same bare Hamiltonian. I will fix that. And then I will let you change all the couplings, I mean the interactions with the thermal environments. You can do that. And then you can choose either to use, for example, a driving here or just a classical work source. And apart from that, you can in this kind of systems, in the weak coupling limit, which is like basically the standard case in which you use Lindblad-Maxter equations, you can show that what's this? I don't know the. Yeah, I don't know the password. So okay, you can show in this limit, for example, if you compute the average heat currents in the system, you can show that they will depend only on the populations of the density matrix. And then, even though, for example, in this case, if you have a driving, the power will depend on the amount of coherence. By just using the first law of thermodynamics in the steady state, you can somehow know that if you have a system that is a classical system that has no coherence in it, but has the same populations as the quantum one, you will mimic not only the heat, but also the power in this case. So what we will fix are the thermodynamic resources, and we will try to see in which case, under which conditions, the classical system can have the same populations that the quantum thermal machine. And to make it more clear, I will show you more or less the process in the case of having Hamiltonian-induced coherence. You go, for example, in a system like this, if you go and solve the equations of motion, you will find something like this, in which you will see that the contribution from the coherence is in this imaginary guy here, which value is going to be given by this equation here, where here I'm considering the tuning for being like as general as possible. And when you force this to be in the steady state, you find that the net effect of Hamiltonian-induced coherence is pumping population from these two guys at a given rate, something that you can mimic by introducing an stochastic transition in a purely classical dynamics. So by just doing this, in this case, we don't have to tune any other parameter. We just introduce this transition and we remove the driving. It's like putting a classical work source here with no bias that give you transitions at this rate. You have a classical system that is using the same temperatures, have the same bare Hamiltonian, have the same populations as the quantum system, and the only difference between two of them are the non-diagonal elements of the density matrix, are the coherence. So with this in mind, and having into account that first moments are going to be equal in the two cases, you find that in order to see any difference between the two cases, you have to go to 2-second moments at least. You have to look at fluctuations. So I will define this new witness as this relative fluctuation ratio, in which you can see that if its quantity is positive, I will say that the quantum system is much more precise than the classical one, and if it is negative, quantum will lose against our classical system using the same resources. So with this, now, well, this is just a summary. We match the incoherent resources, as I said. We compute, this is important, we compute all the thermodynamic quantities analytically. We use full counting statistics, and we find analytical expressions for the heat, the work, and the variance of all the currents. And we will compute also the TUR, the thermodynamic uncertainty relation, to see if it is any difference between what predicts this quantity and what we see with our approach. Just with this, I will introduce our examples, which are basically one in each of the types of coherence. We will consider just a 3-level amplifier, which is basically you have an up transition with a hot bath, then you go down at a given rate with a cold bath, and then you perform some work on an external field. Then you have a 3-qubit refrigerator, which is, I think, the first thermal machine that was introduced in the, well, no, the first one was this one, but this is also a very famous one. And the good thing about this system is that it is autonomous, because if for some people, if you have any advantage here, they will tell you that it is inside, that you are pumping energy continuously in the system, and this is not fair. But here we can test also the autonomous case. And then we have this simple 4-level engine in which we have these like collective transitions, and we will see some noise-induced coherence in this case also. So yeah, with this I will go like rapidly in the examples. This is the Hamiltonian for the case of the 3-level amplifier. You have this driving, this after the microscope, the proper microscopic derivation, you find the Lindblad operators, and then with analytical expressions, what you can do, or what we do, was to perform a Monte Carlo exploration of the whole parameter space, and we designed all the plausible machines, classical and, well, all the possible quantum machines and his classical counterparts, and we compare them. And we found that for all the parameters that we try, the quantum system is much more precise. As we go more and more out of equilibrium, it is much more precise than the classical one. And you can see, for example, for some parameters, I am plotting the value of the TUR. And you can see that in this whole region, you are not violating the TUR. Inside here, you are violating the TUR. But you find that also in the classical reachable thermodynamic region, you can be much more better in the quantum case. Then moving to the autonomous one, you have again this Hamiltonian, this flip-flop interaction, the proper Lindblad operators, and you perform the same Monte Carlo exploration. This is something very nice. I think that right now it is well known in the community that in an autonomous system you cannot violate the thermodynamic uncertainty relation, even though if you have coherence. Some people think that a key ingredient is to have, let's say, energetic coherence. So if you just look at this witness, you will say, okay, this refrigerator is as good as a classical refrigerator. But no, what you find is that, again, you don't have as much improvement as in the case of the laser, which is something that you would expect. But again, you find that in all the configurations that you try, the quantum machine is better. Then moving to the third case, which is the case of the 4-level noise-induced heat engine. Here you have something funny, which is like when you derive the classical analog for this kind of dynamics, you find that what you have to do for your classical system is to tune the interaction with the environment. You just change a little bit the interaction, the spontaneous emission rate, and well, the interaction with the coupling with the bath, and then you can mimic the quantum system. But it is not possible always, because if you look here, this equation is showing you that you have detailed balance and everything is okay, but what you find here is that this quantity can be negative for some parameters, telling you that trying to mimic some populations in some regions of the parameter space with a classical dynamic is not possible. You will get like negative transition rates that for some people is related with, for example, having non-Markovianity. So somehow, for some For some regions in the parameter space, you cannot find a classical dynamics that can mimic these populations. Again, you find that in this case, since you don't have any external input of energy, you cannot violate the thermodynamic uncertainty relation, but you see that it is more a case-by-case comparison, because you can have either cases in which you are worse than being classical, and also cases in which you are better than the classical case. And then what you can think, if you are like a little bit picky, something that I am, is like, okay, we have just seen in the other case that we see like always improvements. You can say, okay, but you are looking just at two toy models. I mean, they are like important, but it's just two cases. It's going to be like always like this. Okay, the problem if you try to tackle this proof is the problem that if you consider an arbitrary quantum system, the dimension of the Liouvillean of this guy can be like whatever, can be huge. So somehow you have to fix dimension. And I mean, the long history short is that we managed to prove it analytically, that in any case that you have Hamiltonian-induced coherence, you would be better than the classical analog that we define, always that you are out of equilibrium, and the quality is just recovered at equilibrium, something that you need, because they have to be the same, since they have the same steady state populations. And the proof, just a sketch, is that we realize that outside of the coherent subspace, what you have in the steady state is just a classical dynamics. You just have jumps between systems. So if you think about this in terms of quantum trajectories, let's say, for this transition here, that is the one that you are monitoring when you consider full counting statistics, what you see is that the state of your system make an excursion in a classical region, let's say, and then with a given rate, he comes back. So you can put all this part of the dynamics inside of what we call a coarse grain state, and then we can use this to fix dimension and to tackle and solve the problem analytically and derive it in a form of a theorem / result. That's all. I think I don't have too much time, sorry. Oh. Just a quick, this is the paper, and for thermal machines enjoyers, I give you here our most recent preprint on optimization of thermal machines in general. You will see quantum Carnot cycles, power plants. It's like very pedagogical if you want to read something.
Okay, any questions? I see one there, yes.
Okay, thank you for the talk. I'm wondering, what is responsible for the violation of QI in your system?
You mean here?
Yeah, here, and...
I mean, I think what is responsible is that it does not, I mean, it's a quantum system and the TUR is derived for classical Markov processes. So in principle, you don't have to follow it. For me, the interesting part is that even if you are in a quantum system with coherence, but you don't have a driving, you cannot violate it. But in principle, you can violate it because since the bound is derived just for classical system, because the one that I am trying is the one for classical Markov processes, not the quantum TUR. You need to, in the derivations for the quantum case, you will have like an extra term that also takes into account coherence.
Yeah, and my second question, you mentioned that in an autonomous system, it's kind of impossible to violate TUR. But for example, there is a relatively recent paper of Patrick Potts and Kasper Prech, where in a double quantum dot setup it was demonstrated.
And it was autonomous in a sense that it has any, maybe I failed because I remember that there was a paper of, I think Patrick and Gabriel saying that an ingredient for violating the TUR was coherence in a subspace that has a system with different energies. But I'm not sure. I have to check this paper.
Okay, thank you. Thank you for the nice talk.
There's another question over there.
Yeah, thank you. It was very nice. But I remember Gabriel Landi has some quantum TUR, no? Have you checked if...
Yeah, indeed, they have a paper. No, it's not Gabriel, but Patrick has a paper with this system in which they show that you can violate the thermodynamic center relation. And they tried the quantum version of that, and they.
Gabriela, if I remember well, derives a TUR for quantum systems. So there
Yeah,
is
but
another.
I mean, I have not.
That cannot be violated, of course.
Yeah, I mean, yeah, I
I
will
don't
check
remember,
it,
I
and
saw
I
it
will
the
see
same
that
year.
it would be like follow it all the time. No. But it was, what I was saying is that I think it was already checked in the paper that they show that this system violates the classical one. They checked the quantum one in the same paper.
All the TUR I've ever seen at some point gets violated.
Yeah, I mean,
Poor TURs. But the fact that you can use this violation as a witness of quantumness is very interesting, and I wonder if you can generalize this in a higher hierarchy of quantumness, if you can show.
well, indeed, I think that, I think that what we see is that more is that comparing just with the 2UR, since it is like a black box, it's not very informative. I think that what we see here is that if you go to a more like, let's say, direct comparison, just having the only, that you see that the only difference is that you don't have coherence in one of the cases, like with, for example, with the relative fluctuations, this witness that we define. I mean, I think that in this case, what you have is the certainty that what you are seeing is due to the effect of quantum coherence. And in this case, as you said, I mean, all the TURs at some point are violated. So
Sure, but if I understand your result correctly, the violation in this case, the violation of the TUR is a witness of coherence.
Can be
of
used, yeah.
quantumness, right?
yeah, but
And the fact that and you just said that it's a black box.
I mean, the 2UR by definition is a black box in the sense that it's just it's just a relation between the quantities. It's a trade-off, but you don't know.
Well, I have to measure.
Yeah, you have
some
to.
current.
Yeah, but this is a black box in the sense that I can put my machine inside of something and I don't know what is happening inside. I just can measure the interaction with the thermal environment, and I would know. I can compute the thermodynamic center.
Okay, maybe in the interest of time, we can have this discussion later.
But
Let's
I
thank
said black box
Jose
in
again,
this sense.
because nobody else was listening. Okay, the next speaker is invited. Yes.